Okay, we start at example 5.7 last week. So we are looking into the problem of two line charge. We want to find the potential and electrical field distribution around two wires of opposite electrical charge. So before we look into the problem of two wires, let's look into the one single wire configuration. So here we have an infinitely long straight line with uniform electrical line charge density, low sub L0. And because of the geometry, we can think of the line is placed on along the z-axis. So because of the geometry, because of the actually symmetric geometry, the problem can be described in the cylindrical coordinate system. So the corresponding Laplacian equation look like this. So as you can see, it's a little bit tricky about the derivative along the r direction. So the general solution is shown in equation 5.74. The potential, the general solution for the potential is A times natural log of r plus b. So the next question is how to determine the value for the constant A and B. So of course we need to substitute with what? With boundary condition. So what we know is here we arbitrarily determine that the zero voltage reference is observed at the location of R sub 0. So we determine an arbitrary position for zero voltage reference. For this particular, for the cylindrical coordinate system, it's inappropriate. It's inappropriate to place the zero voltage reference at infinity, which will cause a problem because of the natural log operator. So here we assume the zero voltage reference is at R0. So the potential V can be expressed as A times natural log of R over R sub 0. Of course, we still haven't found the value for the constant A, but we kind of simplified the expression. And what we know is the gradient of V, the negative of gradient of V is the expression for electrical field vector. So the electrical field vector can be derived easily by taking the gradient, which is a derivative along the r direction, and it's expressed as minus A over R. And as you can see here, the electrical field distribution is actually symmetric. It's pointing outward from the z-axis because it's directed, as the circle shows, it's directed along the r direction, and its magnitude is inversely proportional to the distance r, while a constant A is still need to be determined. Then what can we do to determine the constant A? We need to utilize other known information. In this case, we know the electrical charge density along the wire. So we use the integral form of Gauss's law of electrical field. That is the equation shown below at the bottom of the slide. The closed surface integral of the electrical flux density equals to total charge enclosed by this cylindrical surface area. So the total charge will be the length the length of the wire times the charge density, rho sub 0. And the electrical flux density will equals to the permittivity epsilon times E field times the surface area, because we know this is simply the product of the E field at the cylindrical surface and the size of the cylindrical area, because we know the electrical field, the magnitude of the electrical field intensity is the same along this cylindrical surface. All right, so here is the amount of electrical flux density at the cylindrical surface, and this is the cylinder area, and it equals to the total charge enclosed by the cylindrical surface. Then we do a little bit massage of the equation. We can find that the constant A equals to minus of rho sub L0 divided by 2 pi epsilon. So replace A expression into the potential expression. We have this. The voltage potential is rho sub L0 divided by 2 pi epsilon times the natural log of R sub 0 divided by R. The zero voltage reference distance R sub 0 is a little bit disturbing in this expression, but in the next few slides, I will show you how to get rid of this for a two-wire case. And well, what really matters is here is the expression for the potential, electrical potential. But what really matters is electrical field intensity expression. So taking the gradient of V, you end up with the expression below, which is exactly the same as what we have in chapter 1. Okay, we already done this problem, this problem in chapter 1, and it's a little bit time consuming to derive the result. But as you can see here, the result is the same. The electrical field intensity is inversely proportional to the distance r, and is proportional to the line charge density, as you can see here. So let's go back to the two-wire problem, but you need to pay attention that for this particular case, one line is displaced with positive charge, while the other line is placed with negative charge. And the charge density are the same on the two lines, okay? In order to determine the final question for this problem geometry is we need to know the capacitance for this two-wire structure, okay? So you need to keep in mind about this. All right, so here we have line charge density on this wire and this wire, and they are situated away from the z-axis, and they are located on the x-axis, and the distance from the center of the line to z-axis is b. And therefore, here we place a random So you can substitute the single line potential, the expression for single line potential, such which is shown in the box on the top right, and you substitute. And for here you can pick up an observation point randomly in this space. So the distance from the observation point to positive line is R1 and is R2 for the negatively charged wire. And because of the charge polarity. One is positive, the other is negative. So here you have the minus sign because of the negative charge. So substitute with the known expression for single wire data, you end up with this this expression. This is the expression for the potential observed here due to the presence of positively charged wire and negatively charged wire. And in the equation, you have R sub 0,1 and R sub 0,2, which are zero potential location, reference, zero potential location, which are the voltage reference. And they can be, it's kind of clumsy to choose two different positions for the case because they are located in the same space. So therefore, we can choose a common position for zero voltage reference. So intuitively, naturally, it's convenient to choose the z-axis, which is the has equal distance to positive line and negatively charged line. So we choose z-axis as the zero voltage reference. Okay, so in that case, R sub 0,1 and R sub 0,2, which are the distance from the wire to the zero voltage reference, are the same. So this equation can be further simplified as this, equation 5.77, using a common voltage reference point, that is the z-axis. The voltage difference built up by the positive and negatively charged wire can be expressed in this equation. So as you can see, because the two wires have same line charge density of opposite charge polarity, so the voltage difference built up by the two wires can have a common a simplified expression like this. So take a further look at the expression for the potential V. We know that the voltage difference is proportional to the line charge density low, and is a function of what? It's a function of R2 over R1 ratio. That is the distance to the negatively charged wire over positively charged wire. So as long as the R2 over R1 ratio is the same in this space, they should have the same voltage, which means according to this equation, you can draw the so-called equal potential loop, equal potential locus from this expression. So let's, and so it's look like this. You're looking from the top. You're looking from the top to bottom. So those closed loops, these closed loops are the so-called equal potential circles. But in the 3D space, they are cylinders, right? They are cylinders in parallel with the z-axis. So in the text, it's referred as equal potential surfaces, which are equal potential cylinders, okay? And let's go back a little bit. So suppose the ratio R2 over R1 is K. The value for the R2 over R1 is K, okay? If you have the same K value, same R2 over R1 value, you should have the same voltages. So, so the top equation is what? the denominator, okay, the ratio here, the top is the R2 distance. Okay, so suppose on the XY plane you have an arbitrary observation point. The coordinates is X and Y. And the B is located at the distance, this is the distance to minus B coordinate, which is the location over the negatively charged wire. So here is the square of the distance of R2. And the denominator is the square of distance R1. So on the right-hand side of the equal mark is K to the square, okay? So if you massage this equation a little bit, you end up with this equation over here, which can be further organized as this one. And here is the equation for circles. X minus something to the square plus y minus 0 to the square equals to the square of the radius. So the center of the circle, the coordinates of the center of the circle can be found in this equation. The y coordinate of the circles are always 0, while the s coordinate of those circles are moving according to the k value. So which are the direction of the k? Which is the direction of the circle center movement in the x-axis? Well, it's actually moving outward. So the red arrow indicates the center of the circles moving outward, and those circles, the circles with the highest voltage, starting from the left-hand side over here, because this is the positively charged wire. This one is the negatively charged wire. So the potential, the lowest potential that you can find is near the neighborhood of this negatively charged wire. The corresponding K values are 0 and infinity. Okay? So can you guess what happens if K equals to 1? K equals to 1 means R2 over R1 equals to 1. That is the equal distance from the positive and negatively charged wires. So if K equals to 1, it's corresponding to this straight line over here, which has an infinite. If you look at it, K equals to 1, what is the center position on the x-axis? Infinity. Okay, so the center moves to negatively infinity. Yep. So if K becomes a value greater than 1, then the center will move from positive infinity back to this position. Okay? So according to the equation, you can find well, you can actually draw the equal potential surfaces, equal potential surfaces on the equal potential circles on the XY plane. So here are the centers. So as you can see, or as I remind you last week, the geometric center of the cylinder and the highest potential position within the cylinder are not the same. Distance, the B is the distance from x-axis to the positively charged wire with the highest voltage. and D is the geometric center of the cylinder. Why there is a difference between the two? Because of the presence of negatively charged wire on the right-hand side. Okay, so if you remove the negatively charged wire, the space is occupied by the positively charged wire all by itself. Then in that case, the highest voltage reference position and the geometric center of the wire will be in the same location. However, in this scenario, in this two-wire scenario, because of the presence of oppositely charged wires, the centers for highest potential and geometric centers will have a small difference along the x-axis. All right, so what do we have here? Okay. This box tells us how to find the voltage on the surface of the wire. Okay? Because on the surface of this wire with a radius of A, okay, this wire is not infinitely thin. It have a certain radius. The value of the radius is A, and it must be the same with equal voltage surface. Otherwise, if there is a voltage difference on the circumference of the wire, then the charge will move. The charge will move until you have until the circumference of the wire has an equal potential. Okay. Otherwise, if the voltage potential are different on different parts of the wire circumference, well, the voltage difference will move the charge so that it reach a balance. Okay, so as a result, the radius, not the radius, okay, the position, that's the position on the in this XY plane must have you can use this geometric value to find out the corresponding K value for this case. So here let's review the problem of example 5.7. All right, so according to the equation and the K value, as we know, so here are the expression for the voltage on the surface of a positive and negatively charged wire. So to the top is V plus. V sub plus means the voltage on the circumference of positively charged wire using this expression. And V minus, which is the wire to the right, can be expressed like this. So the only difference between the two is the positive and negative sign over here. So you can show that this can be expressed like this by taking out the minus sign to the outside. Okay. Well, actually, what you can do is do the product of the two components in the natural log function. And you will find that this is just the inverse of that. So that's the reason why you can replace this with this and a minus sign on the outside. So if you use the two expressions for V plus and V minus, then the voltage difference between V plus over V minus, which is V sub 0, can be expressed like this. Okay, the 2 goes away because you double the voltage potential. One is positive, the other is negative. They have the same voltage magnitude, but opposite. But the signs are different. Okay, so you take the difference of the two, you end up with this expression. And another thing, so now we have the expression for the voltage difference. We can find out the total charge per unit length per total charge. That is the charge line density, line charge density, low L0. So according to the definition of capacitance here, you have the expression for per unit length capacitance. And this thing can be expressed as this, the arc hypercosine of D over A. So you need to know how to find out the value with calculator, okay? Provide that you have the D value, A value, or D over A ratio, you should be able to tell me the number for the arc hypercosine of this D over A ratio, okay? So this is the expression given in table 5.2. All right, so let's move on to the next topic. Let's talk about inductance. Okay, so far we have focused mostly on capacitance. Here are the, so here we will look into the concept of inductance. So the title of this slide is internal inductance. Okay, so you will learn what is internal inductance, what is external inductance, self-inductance, mutual inductance. So we have a couple of terminology to be defined and to be introduced. So in the if the conductor in a given configuration are not perfect in what? Perfect in conductivity, then the current flow will goes into the volume of the conductor for alternative current 对于交流电来讲那个假如你是在完美导体上面跑交流电讯号，那所有的电流都只会存在在完美导体的表面。但是假如不是完美导体的话，那就会有一部分的电流，一部分的电场吃进去你个。So if you have a DC line current, DC current, it may be evenly distributed across the cross-section of the conducting wire. However, for PEC, perfect electrical conductor wires, under the AC condition, you will only have surface current. However, if you have a conductor with finite conductivity, then the field and the current density will goes underneath the surface of the conductor. So what is internal inductance? Internal inductance means the current within the inductance built up by the current within the conductor. Oh. We know that because magnetic field is directly proportional to the current distribution. Okay, so you can separate, well, it build up magnetic field along this wire. Some of the magnetic field are contributed by surface current, which are located on the outside of the conductor. Some of the magnetic field are built up by current within this conductor. Okay, so the so-called internal inductance is associated with internal field, which are produced by currents underneath the surface of the conducting wire. All right. So the expression for this is the so-called external inductance per unit length, and it's expressed as the arc-hypercosine of D over A. Okay. To obtain the internal inductance, we have to take into account of the fact that different flux lines in the volume occupied by the current distribution link to different partial amount of the total current. So let's check an example. Example 5.8, we try to compute internal inductance of a cylindrical conductor. So here we have a cylindrical coaxial configuration. You have an you have a conducting cylinder on the inside and a conducting a circular conducting surface on the outside with radius b. And for the inner conductor, the currents are evenly distributed on the cross-section area of the inner conductor. So you have a current density of J sub 0, and it's the same within the inner conductor, within the radius of A. So we want to find out the internal inductance due to the inner conductor. So what we can do is, first we find out the magnetic field intensity associated with the current within the inner conductor. So here is the expression for the magnetic field intensity at a position R. First we know that the geometry is actually symmetric around the z-axis. So assuming that the coaxial cylinder is positioned this way along the z-axis, then and the current is flowing in the z-axis direction as well, then the magnetic field will go around like this, which is in the phi direction. And using the integral form of Ampere's acoustical law, we can find out the amount of magnetic field intensity is associated with the amount of total current enclosed by this cross-section area. So the expression can be simplified as J sub 0 times R over 2. And the magnetic field is on the phi direction. So we can calculate the total magnetic flux passing through this surface. I'm not calculating the magnetic field passing this surface. Well, actually, in fact, there is no magnetic field passing through this surface. All the magnetic field directions are pointing this way. So we are computing a surface expanding by r equal to 0 all the way up to r equals to a. So it's a rectangular strip. The width is a, and the length is proportional to the total length of the wire. So we only calculate a per unit length area. All right? So we know that the magnetic field intensity is more on the inside, is larger on the outside. So we have to perform an integral over this surface. Okay. Okay. So the total amount of magnetic flux passing through the area of a small width can be calculated as the product of magnetic flux density and the area, that is L times dr. And here's the expression for magnetic flux density, which is J sub 0 r over 2 times mu. Okay? So the phi I, the differential magnetic flux in this strip area can be expressed in this form. Then after taking the integral of this, okay, that is what? Okay, taking the integral of this, where n is so here we need to define n. N is the fraction of total current I linked by the flux. We know that the flux is proportional to the amount of current enclosed by this region. Okay, so n will becomes 1 if you are standing on the outside, on the surface of this cylinder, and if the observation point r equals to half of a, then you only account for 25% of the current, right? Now, so it's proportional to the area size of your observation point. Okay, so n is the ratio of the total current within your observation point with respect to the total current I. Okay, so that will be the area ratio of pi r to the square over pi a to the square. Now, so substitute n into the integral of this, you can find out the amount of internal flux linkage associated with the current I. So after performing the integration, you find out it's equals to mu times J sub 0 times a to the square over a. Okay? So the required internal inductance per unit length can be found with the definition of inductance, that is the total flux phi over total current I. So for this particular case, in the DC situation, the internal inductance for this current distribution is mu over a pi for homogeneously distributed current in this case. The general expression for the internal inductance will be this, okay? And here is the expression for external inductance, okay? Well, actually, I do not like this part of the textbook. I mean the calculation is a little bit not that important, huh? So for this case, I will encourage you to understand the definition for internal inductance and external inductance, which you can find in my slide. You probably won't have this kind of calculation problem in the midterm. OK， 好，我个人不是很喜欢这边的部分啦，哈，但因为第一个啦，对于我们现在一般来讲，我们都是以交流讯号为主了，哈，所以 internal inductance 的部分其实是比较小的，不是那么重要的啦，哈，所以，然后课本这边讲的又有点，我觉得有点乱了哈，因为后面没过几页又出来一个 n 哈，那个定义又完全不一样，在讲不一样的东西哈，我觉得比较伤脑筋哈，所以这边的话，你大概就是搞清楚什么叫做 internal inductance， 什么叫做 external inductance。啊，定义搞清楚啊，我大概比较不会考计算题啊。So here are the summary for internal inductance and external inductance. Okay, and for the case of a perfect electrical conductor, because you have only the surface current, then you will have only external inductance and no internal inductance for perfect electrical conductor. Okay. And if you are talking about alternating current signal, you probably don't have to worry about the internal inductance part. All right. So, all right, I think we will end up here. We'll talk about mutual inductance tomorrow.